All right. Hello, everyone. Hi. So there's no batteries. This one also has no batteries, and this one has no batteries. All right. Hi.
Oh,
So
it's being connected.
thank you. Okay. All right. So the agenda for today is share the screen.
3153. How can I help?
Hey, we are out of batteries for the microphones.
Okay, there's no extras
No.
around in the pouch or anything?
No, there's no pouch, in fact, but like in the compartment, there's nothing as far as I can tell.
Okay, understood.
All right. Okay, thank you.
Are you on the last one? Do you have nothing at all?
No, I got nothing. Yeah, so if you could bring some at some point, so I'm shouting in the meantime, it's okay. All right, okay,
Gotcha. We'll send some ASAP.
thank you. Okay, all right. Hi, everyone. Yeah, I'm not going crazy. There is like a button you can push to talk to someone on the lectern. Okay, all right. So the agenda for today is we're continuing talking about the memory model. I apologize that the website is not exactly up to date, but there are notes on the website about the memory model, which I'm actually kind of proud of. So you can read those. So this is that. So it still says 2022, but it's still true today. So what we're going to do is we basically started material from the notes last time. Today, I'm just going to finish up the material from those notes. We'll have kind of an active learning kind of exercise on Wednesday just about this. So not new material, but new exercises. And then today, if there is time, I'm also going to do a bit of practice with problem solving along with introducing a little bit of new material. To remind people, the midterm is on Thursday at 9:10. It's going to be 1 hour, 45 minutes. So I was asked about an 8-sheet. Now, if you look at past year's 8-sheets, they basically have stuff that we haven't yet covered this year. So it's not kind of much with that said. So kind of a lot of this is kind of STR dot, which we just have not done. Now, the reason I'm including this in past years was to make sure that people are not freaking out, oh, like, do I have to memorize all this stuff that's in the documentation? And the answer is, well, no, you can just look it up. This year, we just haven't covered it yet. We will either kind of this week or next week if there's not time this week. Now, this stuff we have covered mostly, so I'm happy to include it. I don't think it's much, but you know, if you want, yeah, sure, it's going to be handed out together with the midterm this year as well. The usual way that they treat those kinds of 8-sheets is you get what you get. It's the same as if you looked it up on the internet. So I never answer questions about the 8-sheet, nothing like that. You just treat it the same way you would treat something you just Googled. So, okay. So this is that. So that's going to be included. So for example, I posted kind of a sample one from 2015. It was the same every year. Since then, it's just that this year, the midterm is a little bit early, and we're in fact going a little bit slower than in past years. So and the midterm is earlier. So for that reason, we haven't covered all of what's on the reference sheet. So if you look, so STR dot, we just haven't done. So this stuff we have done. This we haven't done. So this is also to do with strings. And then like most of the stuff here we've done. But again, kind of not super useful. The reason it's there is just so that people don't worry about, oh, like I have to memorize all this stuff. There's nothing really that you have to memorize. Now, at least kind of to the extent that you're comfortable with the coding back exercises, like you probably memorized everything there is to memorize if you're comfortable with like even the warm-up exercises. Sometimes like with lists, it's useful to know like that there is like dot index, whatever, okay, and it's gonna be there, how to use dot index, yes. So this is like the 2015 reference sheet. Yeah, so you will, so not the str dot because we won't have covered it by the end of today. So it makes no sense to include it. Okay. So, but everything else, but like most of the handout is just like str dot stuff. Okay, all right. So back to the memory model. So I want to, again, kind of, we'll do kind of several goes at this because like this is one of the more difficult aspects of this class. So I think it's worth going over again. So I'll do aliasing again for a bit, and then we'll do globals and locals and how it interacts with aliasing. So aliasing. So what is aliasing? First of all, it's two variables referring to the same address. How does aliasing happen in the ways that we've seen? Well, you do something like L1 is 1, 2, 3, and then you do L2 is L1. So what this does, what this always does, is if you have an equal sign and on the left-hand side is a variable name, you have created aliasing. The reason is like this. So when you have your variable table, and in your variable table, you have variable name and you have address. And let's say L1 was something previously already, L2 was something previous already, so that you're not adding anything, that's not really changing. And then you have the memory table. And this would be address value. And this is just, so here it's just whatever variable names come up. Here it's usually in order. So I usually start with 1032, not for any, well, for a reason, but not for an interesting reason. So something like this. So in order to be able to store 1 to 3, you need to figure that 1 and 2 and 3 are somewhere in memory. So might as well assume that they're here. So in general, if you're creating a new list, you would first put 1 and 2 and 3 in memory. 1, 2, and 3 are special in some way. We'll see how in a second. So L1 would look like this. So it would be at 1032, at 1064, at 1096. So in memory, when, hello, thank you. So thank you very much. Bye. It's like Uber Eats, but free. So put it on my tab. So one. Well, if it worked, that would be 1. One, it's not working, is it? Well, that really is like Uber Eats. All right. Well, it says enabled. Okay, I give up. Okay, all right. So this is like this. And now that we've put the list L1 into memory, so I hope, so are you okay in the last row there in terms of hearing me? Okay. So once this list is in memory, we can say, okay, L1 is at 2024. Now, what happens when you do something like this always is that something from here gets copied. So in this case, at 2024 gets copied to here, right? So it's always just mechanically, always copy the right-hand side onto the left-hand side means look up what address the right-hand side is and copy that address to whatever is the left-hand side. And here, like, of course, now L1 and L2 are both literally this list. So of course you go L1 at 0 equals something new, that's gonna affect L2 at 0. Right, so L1 at 0 equals 2. Well, that means that you go to L1, L1 is this list, L1 at 0 is this guy, so now it's 2. And again, what do? We say, what address is this? This is 1064. So copy 1064 to L1 at 0 to here. So this is now 1064. And then naturally, L2 at 0 is also 2. Of course, couldn't be anything else. All right, so that's the basic idea of aliasing. So how can you, well, so will there be memory stuff on the midterm? So to the extent that they will have covered it in the next 32 minutes, yes. Okay, so I should also say that on Wednesday, we will have a worksheet that's gonna be about this. So you might argue that Wednesday is included. Now, there's not gonna be new material introduced on Wednesday, but we're gonna practice material from today. So, okay. So L2 at 0 now is also 2. So how do I avoid it? So one way to do it is to say L2 is equal to L1 dot copy. So what dot copy does is it creates a new list with the same contents as L1. Okay. So what does it mean? Well, it means that if we say this is the right-hand side, we need to put the right-hand side in the memory table. And the right-hand side would be what's on in 2024 now. And then we just put it in any new location. So I'm just copying this. And I'm gonna put it in, so 26 plus 30, so 272. It doesn't matter that it's plus 32. And like you can kind of see that sometimes, like it's maybe if in fact it is a long enough list that like maybe I can't store it, it doesn't matter. Like those addresses are kind of fake. The important point is that copy just take this and it makes a copy, puts it over here. And now that it's here, L2 would be 2072. So now, of course, I say L2 at 0 equals something new. That's not the same as saying L1 at 0 is something new. So the effect of this would be that this is now 1096. And of course, L1 at 0 is not affected. Make sense? So here's the complicated part. This is the basic story of you make a copy. Okay, now L1, L2 are separate. The issue is like this. Let's say that I now make an L3. And L3 is going to be L1, L2. So it's a list whose elements are themselves lists, so similar to what you had seen in the lab last week. Right? So a list of lists. So what does it mean? Well, I need to create this list and I need to put it in memory. So maybe somewhere over here. So this would be 30, so plus 2, so 70, 04. I think I messed up the math somewhere. It doesn't matter what the numbers are. Okay, so L1 is at 2024 and L2 is at 2072. It's always the case that here what you have is addresses. So what happens now if I say L4 is L3.copy? The same thing as before. I put a new list. Sorry, so L3 here is 3004. So I'm now saying L4 is L3.copy. So the same thing as before happens. This guy gets copied again to here, like so. Right? So that's what .copy does, is it creates a new list with exactly the same contents as the old list, puts it somewhere in memory. So here happens to be at 3036. So that means that L4 is going to be at 3036. So what happens now if I say L4 at 0 is equal to, let's say, 1. So what's L4 at 0? L4 at 0 is this guy. L4 at 0 specifically says, go and change this. So we're changing it to 1. So that means that this is 1032 again. But that means that L3 at 0 is also now 1. Why? Well, because L4 at 0 and L3 at 0 are both this list at 2024. So let's make a picture. I started out with 2 lists. So one of them was 1, 2, 3, and one of them was 2, 2, 3. Or something like that. So this is L1. And this is L3. I then said L3 is this guy and this guy. So I'm not copying them precisely because what's going to happen is L4 is also going to be this guy and this guy. All right. So that's what happens when I say L3.copy is L3 used to be the address of this guy and the address of this guy. And now L4 is also the address of this guy and the address of this guy. Right? So if I go L3 at 0, it's this one. And if I say L4 at 0, it's also this one. The idea is I never created any copies of L1 or L2. I just created a copy of L3. So if you look over here, it looks like this, right? So here I have 2024, which is where L1 lives, and 2072, which is where L2 lives. But it doesn't matter if I go L300, L400, it's the same guy, it's this guy. Right? So I change it, well, it changes everywhere. So what's kind of complicated here is, okay, that's like that. But the story from before was you do not copy, they're independent. And that story is still kind of true. L3 and L4 are separate lists. So if you go L4 at 1 is equal to 3. So L4 at 1 used to be a list, but now I want it to be just a number. What's going to happen is I'm going to copy the address of 3, 1096, to L4 at 1, to over here. So now L4 is this and L3 is this. Those are different. So on the picture, this would look like this. This used to be this guy, but now that goes away. And instead, 3 now lives here, the number. Right? So now, of course, like L4 is different from L3 because L4 has 3 as the second element. L3 doesn't know anything about it. So what we would say here is, so L3 not affected. So what we would say is L3 and L4 are not aliases. They're different lists. But L3 at 0 and L4 at 0 are aliases. So if you change the contents of L3 at 0, well, L3 and 0 are definitely aliases, but they meant L4. So you change the contents of L3 at 0, you also change the contents of L4 at 0 because those are aliases. It's the same as changing the contents of L4 at 0. Because they're aliases. But changing L3 at 0 to something else is not the same as changing L4 at 0. Right? So it's a question of, are you saying L4 at 0 is something new, or are you saying go and change the first element of L4 at 0? Does that make sense? Questions? Okay, I'll let you process for a bit.
Say that changing L3 at 0 to something else not the same as changing L4 at 0. So once you change it, does that mean that L3 at 0 and L4 at 0 no longer?
Yeah, that's a good question. So if you make it so that L4, well, here I made it like L4 at 1 is 3. Well, yeah, like L4 at 1 is now not the same as L3 at 1, but you can't even change the contents of 3 because it's not the list. Yeah. I will not ask you to draw a diagram because that's really difficult to grade. Anything else is fair game. You can look at previous tests to see what I had asked before. Of course, the whole point of a test is like to sometimes ask new questions as well. So I'm not guaranteeing that it's going to be exactly the same. Makes sense? Okay, I heard a chime. Does copy mean copy the value instead of address? No, so copy means exactly what we've done. So you do copy of this, that means that you copy this and you put it in some other place in the memory table. Right? So because of this property, because when you do dot copy, then it's not possible that you just copy the address of this and the address of this. This is referred to as a shallow copy. So that's what last time we saw as like L5 is empty, and then like for E in L3, append D, right? So if you do this, that's the same as doing this, right? And the issue here is that if you just append E, that doesn't mean that you've created an independent copy of E. It means that you've taken whatever the address of E was and you just appended it to some other list. All right. So in principle, what you could do is you could say, okay, so let's say that L1 is like 1, 2, 3, 4. And then the shallow copy is going to be L1.copy, or you would do shallow copy is empty, and then you would do for E. So I'll name it like sublist in L1. Shallow copy append sublist. So that's the same. I just renamed it sublist. So if you know that L1 is a list of lists, you know that there's going to be an issue like this, right? So what you can say is, well, rather than append the sublist, I'll append the copy of the sublist. And that would create an independent, completely independent thing, right? So I'll call it like somewhat deep copy. And initially that would be empty. And that would look like this. So on the picture, where is the video? So on the board, it would look like this, right? So you have L1 is 1, 2, and then 3, 4. And then a shallow copy, so FC would be kind of like this. Right, where the arrows mean that shall copy, like it's a separate list from the original L1, but you're not making a copy of this or this. You're just copying the address. Versus saying that the somewhat deep copy, that would genuinely be a separate thing, which happens to be equal, but it would be a different thing. Does that make sense? Now, one kind of theoretical issue is that, well, is it completely a separate thing because aren't like 1 and 1 aliases? The answer is yes, they are. So if you say something like A equals 1, and then you say B equals A, then yes, it's the same thing. A and B are aliases. But it doesn't matter. Why doesn't it matter? It doesn't matter because you cannot say like A0 is something new. Right? So that's just not a thing that, I mean, you can kind of say that if you look in the footnotes in the memory model handout, there's going to be a way to do it that's kind of system specific that sometimes works. But in general, in Python, there is not a way to say, I want to go to the address where the integer is stored and make it be something new. So going back to the memory table, it's not possible here to say, I want to go to 1064 and make this be something other than 2. Right? So the question back is, well, like, what can you do? Well, if you have A is equal to 1, that means that A now refers to 1032. If you now say, I changed my mind, A is equal to 2, well, that's fine. A is now going to refer to 1064. So that's a change in the variable table rather than a change in the memory table. Right? So yes, it's true that you could have aliases for objects that are integers. It's just that it doesn't matter. Make sense? So note that it works exactly the same way with lists. So if you say something like L2 is equal to L1, nothing's stopping you from saying, oh, L2 is now going to be equal to 6, 7 or something. That's completely fine. And that would involve making a new list 6, 7, and then saying L2 now refers to that address. L1 would not care about that. In fact, L1 and L2 are no longer aliases now. Right? Because this is saying make it so that L1 and L2 refer to the same thing. So here this would be take this and copy it over here. L2 is equal to something new means take this and make it something else entirely. So you make this something else. Okay, great. L1 now refers to a different list from L2. They're completely independent again. Okay, so we'll do more practice of that on Monday. So I will, and I see kind of different people take different approaches when on the midterm, on the exam, when they approach those kinds of problems. So some people write out the tables And I think it makes sense. So like the 3 rules that we worked out last time, like you just apply them, you'll get the answer if you apply them consistently. So it works for some people. Now it's laborious and maybe it doesn't work for everyone. So when I myself look at this kind of code and try to predict, I don't like have a table in my head, right? So what I have in my head is something like this picture. Now, the problem with the pictures, with kind of drawing a diagram, is that it's harder to have like, those are the 3 rules, that's how they work. Just apply them when you're talking about arrows and diagrams. So it could work for some people, but it's kind of a little bit more up in the air. So I would say the real rules are what we said in terms of like what gets copied where, like in the variable table or the memory table. However, it's easier to think in terms of diagrams if you have exactly the right idea about what the diagrams should be. So next, so on Wednesday, we're going to practice working with just the tables. I encourage you to also draw diagrams along the way. If you see that what you draw in a diagram corresponds to what's in the table, at that point, you can throw away the tables because they're annoying to think about and just think in terms of diagrams. I do think that like one of the most common things that goes wrong when people do those kinds of things is they don't draw either the table or the diagram and they just trust themselves to do it in their head. Well, like if you genuinely tried it with Python and you know it works every time when you do it in your head, well, sure, fine. You know, it works for me. But it started working for me not right away. I had to practice first. So, okay, all right. So this is this. So I promised that we do calling functions. So we'll do calling functions now. So basically, it's all the same. What you need to know is that when you're calling a function, so when you're calling the function, what happens is the address of this gets copied to the address of this. So at this point, it's that L and L1 are aliases. So as if you said local L is equal to L1. Exactly the same thing happens. So in terms of the tables, one thing gets introduced. So I'll copy the memory table from over here so that I don't have to write an entire new memory table. So here I have a variable table, so I'll do a new thing. So L1 is 567. So I'll put 567 over here. So L1 is going to be 1032, 1064, 1096. That works. And then the variable table, it's going to be L1 is 2024. So when you have local variables, you could have separate local and global variables. So that means that the variable table should be specific to the function. So every time you call a function, like you call a function f, there's also a variable table for the local f variables. So specifically what happens is right now there is a new local variable L. And when you call the function using f of L1, what happens is this 2024 gets copied over to here, because that's what happens when you have take the right-hand side and copy it on the left-hand side. What this means is take the address associated with the right-hand side and copy it to the from the left right-hand side to the left-hand side. So the 2024 gets copied over here. So that means that L at 0 equals 7 affects L1 at 0 as well. Because again, the local L and the global L1 are aliases. On the other hand, L is equal to 7. So this would be like this now, right? So 1096. So you just have one copy of the L or L1. So that means that you go here and you make the 7. Well, they're both 767. Does that make sense? So on the other hand, if you go and say L is equal to 7, what happens is the address associated with 7, 1096, gets copied over here. L1 does not care. Right? So at this point, the local L is equal to 7. L1 is still the same. So there is now a bit of nuance in terms of what happens if you change, well, change in quotes, a local variable. So if you genuinely change it the way we changed integers in the beginning of the class, yeah, it's like this. Like you say L equals 7, well, you're changing the variable table for the local F, for the call to F. It doesn't affect anything. However, you say L at 0 equals 7, you're changing the contents of L. That means you're going into the memory table and changing this guy. Well, anytime you go in the memory table and change stuff, that can affect all sorts of things. Make sense? How do you know if you're going in the memory table or not? Well, if on the left-hand side, you are changing an element of a list, that means you're going and messing with the variable, with a memory table. Because make L at 0 something new, well, L at 0 lives over here in the memory table. On the other hand, saying L is equal to 7 over here, well, you're not changing an element of a list, you're just saying the local variable L is now something new. That does not affect L1 or anything else, just L. Make sense? So one thing that people sometimes are misled about is like, oh, that's lists, because I'm not going to say this word for the next 10 days, but like lists are mutable, integers are immutable. If you don't know about this, don't worry. It's not that. If you know about that, it's not that. Integers work exactly the same way as lists. It's just that with integers, this kind of thing is available. So you can say L is equal to 7 where L is local. You cannot change the contents of an integer in a way that you can change the contents of a list. Make sense? Okay, 3 p.m. I will see you on Wednesday. Bye. Yeah, and so office hours today at 6:30 in GB 119, and tomorrow as usual as well. Hello. Okay.
Like, still lost with this, why for 0, 0, 1, okay, I'll upgrade any change. But for this, I'll upgrade this one.
Right. So if you have, so this is what's called a shallow top, right? So if we have, it's going to compare it, so L1 and the shallow top of L1. There's only one copy of one copy of one. This is like the rectangle here. So if you want to change this guy to something else, well, everything is equal. Like whether you insert it here or here. It's not like you just make a problem. Right? So on the other hand, say one this side is not equal to this, the one is something else, well, that is right. Yeah. That's how see the code that you have. The basic idea is you change the content of this flag. There's only one copy of this flag, so you change the content, like you make something in the type here. Then that's back to shallow copy. The shallow copy just has all the alias of it. Right. On the other hand, if you just say SPF, you that's it. I mean, so that's what we need to change. One is something new. Then one is still gonna be. Right. If you say L1 is 1 0 is something you can change to 5, then that's it. If you change like both this and this, it doesn't matter, like this and this will also change. Right. So your question was the entire thing, like if you start saying L1 is 1 equals something, then yeah. No. So like this, let's change it. So 1 is 1 something new, it's going to be something new, and this is new. If you're going like no 1 is 0 is something new, well then this is new, and this is the content of an alien. Here, so they are still yeah. Yeah. Okay. Well, okay. Yeah. Well, so every integer that's so every integer that's accessible to the program. 32,000. No. Every integer that's accessible to the program. So if you so what's restored is just -5 to 55. And that's really like you were implying is yes, like every one of them is stored. Everything else, if it's used, then you put it in memory in the same way that a float, if it's used, you put it in memory and it stays in memory definitely while it's possible to access it. If Python sees that particular integer is not anymore accessible for memory, then it stops. So I can show you quickly.
Access the other.
So I can show you quickly. So let's say that they do like I is whatever, and then I say like while whatever. Just right. So what you'll see is it just figures out an address for each new one, but you'll also see that it reuses addresses. So, well, I'll just copy and paste, and that's enough. Right. So what happens here is I keep just saying I plus equals 1, so it's like one large integer, another large integer, another large integer, and so on. But there's only one value that's currently associated with that. So Python reserved the right to say, okay, like this is not anymore a number that's going to be accessible. I'll just overwrite that difference.
Okay,
But not right away, as you see. So it doesn't reuse right.
that's like,
That's right.
and also, Python also have its own space, like, I guess, string constants.
No. So again, kind of, you create a new integer in the same way, like here, like those are created on the fly, right? They're not preset. In the same way, like a string is created, you stick it in memory. So it's not like its own space. It's like it's created.
Like, they don't have like a little space, like a dictionary level, like,
No.
he is this, he is this, he is this.
So it is literally a dictionary for stuff that's in memory currently, right? So you go, so here, like you go and say, what's, so it's called like, so you can see like, what's the globals dictionary? And here it says, I refers to this address now. So I can also have like whatever hello, and now there's also gonna be an A somewhere here. Yeah, so there is, so A is hello, so like there is an address. Yeah, sorry. So that, by the way, wasn't an address, that was like the value, but underlying that is an address. Yeah, hi. Yeah. That's right. I mean, like, I mean, it has to be either above or below. And they're really kind of, it's not like, it's neither, right? They're just two tables, and it's just that, like, in my editor, one has to go above and one has to go below. There's no decreasing. No.
Yeah, so when you guys like doing the coding back questions, I
Yeah.
got this a lot where it's like this is index out of range.
Okay.
But then when I do it, like what is it like Python like
Well, I mean, that means that, like they have hidden that statement.
yeah, so like when I looked at the code, I don't see any reason that it would ever be out of range. I'll just like oh, this is
I mean, like usually if it's empty or something, that, yeah,
that's
must be. Yeah, I mean, I don't know this question, but like that's the usual thing.
so like is the auto grader
No, I don't have the test pages on there. Also, it's like pass fail. So I mean, you don't need to worry about it, but like might as well, right?
all right, thank you.
Yeah.